Good afternoon, everyone. Today we will continue with our lecture series, video number 2. We were going to cover section 9.3 and 9.4 for this video lecture, calculating the work done and the work done by spring. As you can take a look at here on my shared monitor, our learning objectives are twofold. Number 1, we will learn how to calculate work done by a constant force in an arbitrary direction. In the previous lecture, we learned to calculate work done when the force and the displacement were in parallel. And today, we will learn a new expression of dealing with a displacement and the forces that have arbitrary directions, so the angle will be involved. And number 2, we learn how to calculate the work done by a spring as an application. Let's do a quick review from yesterday. From the lecture video number 1. Let's do a quick review on what we learned in lecture number 1. We learned what is work, and we learned about what is kinetic energy and their relationship. And by using the work and energy paradigm, I mentioned that we can bypass dealing with individual forces. Now, up until today, we will still be working with the forces and work and energy together. But later on, we will deal with situations and examples where forces are entirely not considered, and we just work with the work and energy paradigm. Now, we also learned that the work is mathematically derived from Newton's second law, and that the velocity, which usually is in time in Newton's F equals ma, we derive the velocity respect to change in position, in change in space instead of in time. And hence we got to this relationship where the work is defined as the integral of a force of respect to a position, and that leads to the other side, leads to the change in kinetic energy. So that we learn that the work done on a single particle system causes the system's kinetic energy to change. In other words, work is what transfers energy in a system by an external force applied to it. All right, so let's continue with our lecture today. Okay, here. All right, so thus far, we dealt with a simplified case where force is parallel to the displacement, as I mentioned. But in general, and we're discussing in two-dimensional space in most of the problems, a force is still a constant force, but a force and the directionality of the force to its displacement may have any arbitrary direction in a 2D space, meaning that there could be an angle component. So the question is, when there is an angle between the force and the displacement direction, how do we solve for this? How does that angle component contribute in terms of calculating the work done by that force? So we're going to take a look at the figure here. So figure here is the situation we dealt yesterday, where the force and the displacement are along the same axis, either parallel or anti-parallel. And if it's a parallel, we know it's a positive work being done. When it's anti-parallel, that's negative work being done by this force. Now, in this case over here, that force and the displacement could have a different angle. And here in this case, we define the direction of the displacement as the original axis, and then the force acting on this particle could be deviating with a certain angle, theta. In this case, how much of that original force component contributes to the work is a question. And that is, we consider if this is the force vector, then we know along this x-axis, or in this case s-axis, the force component there would be F cosine theta. Why cosine theta? Because angle is defined off of the x-axis, or s-axis in this case, so that you have now the force of magnitude of the force is F cosine theta. And then the rest of the part remains the same. So dot ds. And since we're dealing with a constant force in this example, a constant force, and the angle, let's just say, is also constant. Once it's fixed, it doesn't change. Then this is just a scalar. So what comes out is that this basically comes out of the integral. Okay. And then you will have simply ds here, sf, si, and this part we know is F cosine theta. This is S, SF, SI, which is simply equal to delta S. So it is the same expression as what we learned in the previous lecture, except you just have the angle component as a cosine theta. That's the only thing that is being added in a case where you have an arbitrary direction between the force and the displacement. Now, we will use math as a tool also today to develop a little more compact and a generalized expression of the dealing with the arbitrary directions below. But before we get into it, let's take a look at this very simple example, example 9.2 in your textbook. Pulling a suitcase. So a strap inclined upward at a 45 angle pulls a suitcase 100 meters through the airport. The tension in the strap is 20 Newton. How much work does the tension force do on the suitcase? So here, take a look at this figure here. You have the tension force pointing up this way with 45-degree angle, and it is pulling the suitcase over 100 meters direction. And here the tension is, we're told, the tension is 20 Newton. So force that is going to be pulling the suitcase horizontal would be force of the tension cosine 45, because that's the angle off of the x-axis, so that is the x component of this tension. And that is then multiplied by the displacement, which is delta x here, and that would be equal to the work done by the tension. So here, just plug it in here, 20 Newton cosine 45 times 100 will give you the work done by the tension, and then you just can plug it in that into a calculator, and then we're done with it. Okay, so nothing new, a very, very simple a step further from the previous lecture. Let's take a look at this example here. It's a little bit more involved, but not too much. Example 9.3. Launching a rocket. So in this case, we have 150,000 kilogram rocket is launched straight up. The rocket motor generates a thrust of 4 times 10 to the 6 Newton, and is asking us about the rocket speed at a height of 500 meters. So take a look at this free body diagram here, and from this, I can immediately write the sum of forces in y, and that is the force of thrust minus force of gravity, and that is pulling this rocket upward. And by using this route, you can solve this problem actually not involving work and energy at all. Here you know the force of the thrust, and this is mg. So if you put the number here minus mg divided by the mass of the rocket, you will have the expression for the acceleration of the rocket going upward. And by knowing the initial velocity being 0, and now you'd have the acceleration and then the displacement, you can easily solve the final velocity of the rocket by simply using Newton's laws. So again, this is an example that it doesn't necessarily require a work and energy concept, but it's there for us to compare the two methods and get ourselves familiarized with the work and energy concept. So let's try to solve this with work. There are two forces involved. Okay, so that means there will be two types of work being done. So work done by the rocket, by the thrust, is the force of thrust times the displacement that it causes. And in this case, you know the thrust and the displacement is in the same direction. This should give you a positive work here. So that's simply 4 times 10 to the 6 Newton multiplied by 500 meter. And that should give you the work of the done by the thrust. Just getting my calculator here. All right, so just put that into the calculator. We have here, oh boy, 2 times 10 to the 9th joule. Now the work done by gravity is force of gravity times the displacement. In this case, it's minus mg, while the displacement is plus. So this shall give us a negative work. So here we have minus 150,000 times 9.8 times 500. And that should give us minus 7735 times 10 to the 6 joule. Okay, so now the work total is work done by the rocket plus the work done by gravity. So this would be this number subtracted by that one. Which is 1265 times 10 to the 6 joule. Okay, so that is the total work being done, and that the total work being done is equivalent to change in the kinetic energy of the system. So here, this number is equal to the change in kinetic energy. So 1/2 mv final square minus 1/2 mv initial square, and we're given that the rocket is launched straight up from the initial velocity of 0, so the initial kinetic energy goes away to 0. So then you can solve here for the velocity. So it's simply that number times 2 minus. Okay, so I'll just write it here one more time. 265 times 10 to the 6 joule is equal to 1/2 mv final square, and you're solving for the final velocity. Okay? Okay, so same problem, one methodology using Newton's laws, as on the right-hand side, or the left-hand side using work and energy. And now it does appear in this case that using the Newton's law is the choice of simplicity. But again, we're trying to get ourselves used to the system and paradigm so that when we encounter a situation later on where we have to use work and energy to solve, that we'll be prepared for it. Okay, so let's continue here. Now, I mentioned earlier here that we will use a math as a tool to develop a more compact and generalized expression of the work. Now, that mathematical tool is called the vector dot product. And if you have not yet seen a vector dot product, I hope that you have. It's defined as this. So vector dot product, the input is you have two vectors being involved, and this dotted between them is an operation. It's an operation defined that, take a look at this figure here, if you have two arbitrary vectors, and between them, if you put their starting point together, they will have some arbitrary angle alpha. This alpha could be any angle from 0 to 180 degrees to 360 degrees, rather. And in this case, this general situation, the dot product is defined as vector A dot vector B is, you multiply the magnitude of each vector together, and you multiply the cosine of the angle between them. So the vector dot product is AB cosine alpha. This is a promise. This is a convention. This is a definition of this dot product operation. That's what you should do when you're seeing a dot product. Okay, so the input is you're dealing with two vectors. The result, the output, is scalar because A, B are both the magnitude of vector A and B respectively, and cosine alpha is also a scalar. So as a result of a dot product, you start with two vectors and you end up with a scalar. Okay, so that's very important. The output for the dot product, you get a scalar, and you start with vectors. This is contrary to cross product, where what we will learn later on, where the input and the output both have vectors. Okay, so let's take a look at this component. We could always express a vector component as such. So vector A, let's call it has x and y component, because we are going to assume that just a two-dimensional. If it's a three-dimensional, it will have a, z, and k hat as well. But let's just consider for the two-dimensional case here. Vector A can be written arbitrarily as this. ij components, and the ax and ay are the a scalar component. So what does it mean in this term that you have a dot product between A and B? Well, that simply is saying axi plus ayj dotted with bxi plus byj. And here you use a distributive law, multiply each components separately. So you'll have ax, and then you have bx, and then you have I multiply dotted with I. Okay? Plus, let's do the second term here. You have ax, then by, then you have I dot j. Plus the second term, ay, bx, j dot I, and then finally ay, by, j, j. Okay? Now, before we finish this off, take a look at the figure on the right-hand side. So we defined that the dot product is between two vectors, and then you multiply the two magnitudes together and multiply by the cosine of the angle between. Now cosine, we know certain special angles, properties of cosine. So for example, cosine 0, which is in a case where A and B are completely aligned in the same direction, then there's no angle between them. Cosine 0 is equal to 1. So the dot product of A and B is simply AB. On the contrary, if the angle between A and B are perpendicular, cosine 90 is equal to 0. So the whole dot product is wiped out as 0 when A and B are perpendicular. And here, down here, and A and B are pointing opposite directions. Then the angle between them is 180. That's why this is cosine 180 is minus 1. So A dot B is minus A and B. Okay, this property comes because of the cosine property. Now then take a look at here. I, j are the two unit vectors, right? I is pointing always in the x direction with the unit length of 1, while the j hat is always pointing in the y direction with a unit length of 1. So here, take a look at here. I dot I, they're the same, hence pointing at the same directions, so that the angle between them is 0, right? Here the angle between them is 0. So this makes this whole term equal to 1. And here you have, when you cross them, I dot j, ij, their angle here, alpha is 90 degree. So this term goes away as 0. And same thing here, that goes away as 0. Here jj's again, alpha is equal to 0. Here the alpha is 90 again. So this term is equal to 1. So only the first and the last term will survive. So in terms of components, ax, bx, and is multiplied by 1 plus ay, by multiplied by 1. So a dot b in a component version is you just simply multiply a term and the b terms together and add it together like this. This is a definition of a dot product in terms of components. And using this way or using the cosine way, you should get the exact same answer. This is more useful when you directly know the vector and component form. And this is more useful when you know the angle directly and the magnitude between A and B directly. Okay, mathematically the same expressions. Okay, so remember that we said that the work done by a force that has an angle between the force and the displacement can be written as F cosine theta dotted with the displacement here, right? Here the dot is a multiplication, so these are the scalars, not vectors. But in more compact, more generalized form, you can simply describe this as two vectors. Vector of force vector, this is a dot product here, dotted with the displacement vector. This and this, let me just put here S just to be consistent, is exact same definition, right? We have just take a look at that's the definition of dot product. This is just a more generalized and compact form, and it's very useful because we can directly operate between vectors. So let's take a look at this simple example here, calculating a dot product. So you have A magnitude is 3, B vector is magnitude of 4, and angle between them is 30 degrees. So A dot B is simply the magnitude of A and B times cosine 30 degrees here. So 3 times 4 times cosine 30 degrees. That's A dot B. Okay? Very, very straightforward. Now let's try with the component form here. This time, A is this and B is that. And in this time, A dot B, we use a component form. And if you remember the property that we used, we use here, it's simply AX times BX plus AY BY. And in this case, AX is 3, BX is 4, plus AY is 3, and BY is minus 1. So this is 12, 3, so that's equal to 9. So that is straightforward using the dot product with components, and here is with the angles and the magnitude. Depending on the situations, you may use either ones. You should get exactly same answer. Okay, so let's take a look at an actual physical example. Okay, so in this case, a skier is sliding down a slope that is 10 degrees, and the angle between between the force of gravity to the displacement, in this case, is 80 degrees. And of course, the normal force between the displacement is 90 degrees. So 70 kilogram skier is gliding at 2.0 meters per second when he starts down a very slippery 5 meter long. Very slippery here means ignore friction. Ignore friction. 10 degrees slope. What is his speed at the bottom? And let me do this in both ways. The method number one is what we are familiar with using Newton's law. So in this case, the angle of the slope is 10 degrees that we're told. So in the tilted axis scheme, let's call this direction positive for now. You have the force of gravity, which is mg sine theta. Okay, and that's it, right? That's it. That is causing, because friction is negligible, this person to accelerate like this. So here you have g sine 10 degrees will be the acceleration of this skier. And once you know the acceleration, then again, using the kinematic equations, delta x, find a velocity, what we're trying to find out. The initial was 2.0 square plus 2a, you put that number here, and then we're given that the length is 50 meters. Is 50 meters. And then you can solve for velocity. Okay, so that's the method that we know. Okay, now let's solve this with a method. Solve this with work and energy. So method number two. In this case, let's consider the work done by gravity on this skier. That would be the force of gravity dotted with the displacement vector. And this definition is we're using the compact definition that we just learned using the dot product. Okay? And here the force of gravity is mg. That's the magnitude of that. And the displacement, of course, is delta x. And then now we have to use the angle between them, the angle between these two forces, right? This is the force of gravity arrow, this is the displacement arrow, so the angle between them is 80 degrees. So here, we're given that it's 70 kilograms, 9.8, 50 meters, cosine 80, we get we get 5,090.56 about, and that is in joule. And since that's the only force involved, this is automatically a total work. So this we can set that equal to change in kinetic energy. So this case we have 5,956 is equal to 1/2 mv final square minus 1/2 mv initial square. For the initial, you put the 2.0 for the velocity, and for the mass you put the still 70 kilograms. So in this case, you only have also just one variable. So you can solve the velocity final using this way. Okay, so this one was, I think it's almost as long as using method number one. But this is how you can solve this using the work and energy principle. Okay, moving along. Now, as an application of the work and energy principle, we're going to take a look at the spring force, and we're going to derive the work done by a spring, considering the spring force. Now it should come to you very clear that if there is no force, there can be no work done, right? Yes. No work can be done. Force is the medium. So the work is, conceptual wise, work transfers energy in and out of the system. So work transfers an energy of the system via an external force. So the work is done by the force, and the work, which is energy, that translates or transfers energy in and out of the system, in this case in a form of kinetic energy. Okay, so when there is a force, you know this force is capable of doing a work on the system. Okay, so let's take a look at the spring force as an example. Here, the force of spring, Hooke's law, is again minus k, spring constant, times displacement. Okay, so the displacement delta S is defined. Take a look at this figure here. This is the equilibrium length of the spring when it's neither stretched or compressed. Then you could have a spring that is stretched. In this case, we say this is stretching this way, so the displacement is positive. Then the spring forces wants to restore it back, so it's always opposite to the displacement. Okay? Always opposite. And when you want to compress it, the displacement is negative, but the spring wants to push it out. So the force is always the opposite direction of the displacement. So you can imagine that in the spring, the work done would be negative in general, because the force and the displacement is technically done in opposite directions. Okay, so that is the Hooke's law. And now let's take a look at this example. This is example 9.8 in your textbook. Okay, so this shows a spring attached to a 2 kilogram block. The other end of the spring is pulled by a motorized toy train that moves forward at 5.0 centimeters per second. The spring constant is 50 Newton per meter, and the coefficient of static friction between the block and the surface here is 0.6. Here's 0.6 is a static friction coefficient here. Okay, the spring is at equilibrium length at t equals 0. When the train starts to move, when does the block slip? Okay, so first of all, when we have dealing with the forces, it's always useful to draw a free body diagram. So consider from this box perspective. Okay, from the box perspective. We have the force of gravity pulling it down, and then we have the normal force pushing it up. Now take a look, think about this spring. Spring, this is being still. And the spring here had equilibrium lengths, and it's going to be pushed or stretched out this way. And from this point, the spring then of course wants to restore back that direction. But now consider from this box perspective. That restoring force also means that it's providing equal and opposite forces of this pulling it that way. Right? So, in a free body diagram, we can simply, so you can think about what's going to happen to the box. The box will be pulled that way, this direction. And that will be the force of the spring, restoring force back to this equilibrium position. It could either shrink back from this direction or shrink back from that direction, right? And the middle of the spring, that force would feel that's equal, just an opposite in direction. So this box will have a static friction try to put this on hold because the box wants to be pulled that way by the spring. So this would be the spring force, okay? All right, so in that case, we set up the sum of forces in X. In this case, we have, let's consider the force of spring minus static friction, and that is equal to 0. Because we want to know when is this equilibrium is going to break. So here the force of spring is minus K delta S. That is equal to static friction, which is coefficient times the normal force. And of course, the normal force in this case, if you do this, N minus force of gravity is equal to 0. So N is equal to mg. So this becomes mu mg. Okay. Now let's take a look at the displacement here. It's now being pulled out this way, stretched out that way. So in this example, when the spring is stretched that way, we consider that to be a positive displacement. But that is happening from the other side perspective, right? It's going to be it's feeling the stretch from this side. So here we're just going to consider that here is K minus delta S is mu mg. So it's simply you have K delta S mu mg. Okay, so in this case, I can write delta S as divided by K, and here the static friction of coefficient is 0.6, the mass of the block is 2 kilogram, and G is 9.8, divided by 50 newtons per meter. Okay, so this distance will tells me when the spring is stretched beyond this length, it will overcome the maximum static friction and the train will begin to slip, right? So let's see, this is 0.6 times 2.0 times 9.8. So this length comes out to be 0.23 meter. All right, so going back to the situation here. Now, the spring will begin here when delta S is 0. And it's moving 5 centimeters per second out. And we're asked when, the time, the train starts to move, when does the block slip? So you start from delta S equal to 0, and it will slip when delta S becomes 0.23 meters and is moving 5 centimeters of 0.05 meters per second. Then we can determine the time, right? Because velocity, the change we're looking at is 0.230, and the velocity is 0.05. That will give us the time, right? Because delta S divided by delta, let me just write it once again here. Here, this is delta S divided by velocity will give us the time. Okay, so that 0.23 divided by 0.05, it will take 4.6 seconds. Okay, so this exercise example lets you play a little bit with the Hooke's law to get used to about the concept of the spring. So let's now calculate the work done by the spring. So take a look at here. Work is, the generic definition is the integral of the force involved in respect to position, and the position changes from initial to final as general. Now here, for the force, we put the definition of the spring force. Okay. and then it's dotted with ds. Just copy and paste it here. Okay, delta S. Now, of course, delta S is S final minus S initial. So what I'm going to do is simply going to change this part conveniently as delta S, and then I have to also change this part accordingly. Okay, to make that I'm integrating over not just S but over delta S. So I'm changing my variables accordingly. Okay. Now here, k is of course a constant, so constant comes out of the equation, and then you have this integral here, which is just simply delta s respect to d delta x. And that here, let me continue writing here, is simply minus k delta s over 2 square, and then you have delta s final, delta s initial, so you have minus k 1/2 delta s final square minus 1/2 delta s initial square. And that is, when you distribute them out, let me just write it once again here. And we'll put the minus term here, 1/2, and then put the k delta sf square minus 1/2 k delta si square, and that's the expression that you will find in the book, Work Done by a Spring. Here the important thing is this: the delta s final, delta s initial is defined as such. So here is the equilibrium position. When you're compressing it, then you have a change of delta Si. When it's stretched here, you will have delta S final. Okay, so this is how you can distinguish in a situation whether to use delta Si or delta Sf. But here the sign doesn't matter because it's going to be squared. All right, so this is the work done by a spring. All right, so let's take a look at this example to enforce what we have just learned about the work done by a spring. So a horizontal spring with spring constant 85 extends outward from a wall just above the floor level. A 1.5 kilogram box sliding across a frictionless floor hits the end of the spring and compresses it 6.5 centimeters before the spring expands and shoots the box back out. How fast was the box going when it hit the spring? So here, the situation is like this. We have a spring, and a box is sliding that direction. And upon impact, it will have an impact with the initial velocity. And this side, you have the kinetic energy of the box, and it's going to compress the spring. We're given this 6.5 centimeters, so 0.65 meter, and then the final velocity will come to a halt. So the kinetic energy is going to translate into the spring, elastic spring potential energy, which we will learn in chapter 10 about its terms, but it's going to be changed into potential energy of the spring. So here, the work done by the spring is going to transfer the kinetic energy into a spring potential energy. So the work done by the spring is simply, we use the generic definition here, minus k delta s SDS, and that results to the change in kinetic energy, which is 1/2 mv final square minus 1/2 mv initial square. So on this side, we know the final velocity is going to be 0, so this side is minus 1/2 mv initial square. On the other side, let's get rid of the minus sign here. We will have simply k and delta s ds, s initial, s final. And this part is the same what we derived already up here. So I don't have to do that part again. So here, I only have, in this case, this is shrinked inwards. So according to this picture, I'm dealing with just the initial delta Si. So here, this side I will have 1/2 delta Si square. And on the other side, you have 1/2 mvi square. So half and half cancels out, and to solve it for the initial velocity, so I have k delta Si square divided by mass is equal to initial velocity square. So let's put the actual numbers here. This is 85 times 0.065 square divided by the 2.0 kilogram is going to be the initial velocity square. So this leads to the velocity equal to equal to 0.42 meters per second. Okay, so this is an example where you can utilize the work done by the spring, that the work transferred the kinetic energy into a potential energy form, that and the work was that medium, right? So here in this case is a good example of spring constant. Now to finish it off, let's take a look at some conceptual questions from the slide. So we have done this example here. Now, before we move on, there are certain cases where there are some zero work situations. We talked about it, so take a look at the expression that you see up here. In terms of dot product, or in terms of written out or integral problem situation here. A force that does not displace an object does no work, right? This is the case when delta R is 0, the work done will be 0, right? The work would be 0. That's clear. A force everywhere perpendicular to the motion does no work. And that comes from the fact that when the angle here, theta, becomes 90 degrees, then this whole term goes away to be 0. So work becomes 0 when the angle between them is perpendicular 90 degrees. So two cases. Of course, when there's no force involved, can be no work done by that force. That's a trivial case. But if that force does not displace an object, if the displacement is 0, no work. Even though there is a displacement, if the displacement and the displacement happening this way, the force applied is being that way, in this case also, there is no work because the cosine term will take care of that. Okay, so this is the zero work situation. So, for example, a circular motion. You have a force everywhere perpendicular to the displacement in a circular motion, right? Because the displacement always is going, the velocity is always happening this way, so displacement is happening in a tangential direction, while you have the acceleration, centripetal acceleration, so that your net force always points inward in a uniform circle. So in this situation, there is no work being done, even though there is a non-zero force involved and there is a non-zero displacement involved. Okay, So this is a good example where there's a zero work being done in a uniform circular motion. What about this conceptual problem? A crane lowers a girder into place at constant speed. Now consider the work done by gravity and the work done by the tension in the cable, and which is true. So here, a girder, this is a crane, is being lowered, right? In this case, you have the force of gravity down this way, the force of tension the opposite direction, but the displacement here is negative. And we know that force of gravity direction is also negative, so the work done by gravity has to be, the work done by the gravity is minus together has to be positive. But here you can see that the force of tension and the displacement is in opposite direction, so the work done by the tension has to be negative. So when that would be B. Okay, so downward force is positive and negative work, etc. What about this situation here? Robert pushes the box to the left at constant speed. In doing so, Robert does what kind of work on the box? Constant speed. What does that mean? Constant speed means that the net force is 0, right? Now, since the net force is 0, does that mean the work done by Robert is 0? Well, let's consider what's happening here. Robert is pushing this box that way, while the friction force is opposing Robert. All that this is saying is that the net force, so the force of Robert plus this is equal to 0. It does not mean that individual forces are 0. So the work done by Robert still is non-zero work. Okay? So in this case, this displacement is this direction while the force is also pointing the same direction. So the answer would be positive. Positive work. Okay? So that's how you can think about conceptually between forces and the work being done on it. Let's see. This we have just talked about in zero work situation. When you have a car turning a corner, we know that static friction causes a centripetal acceleration. So the static friction is pointing towards the inward, towards a circle. And in this way, even though this is not equal to 0, and this also is not equal to 0, the angle between them is 90 degrees, so the work done by the static friction is 0. Okay, and lastly, we talked about it several times, the transfer of energy to a system by the application of an external force is called work. Okay, work is what transfers the energy to a system via an external or force being involved there. Okay, so that concludes the lecture for today. Let's just recap what we talked about today. We learned about how to calculate work involving forces and displacement directions to be arbitrary. And then we also learned about the dot product and how to express work in terms of a dot product a little bit more in general way. I will write it here once again. Work is simply the dot product between two vectors, right? Between two vectors. Okay? The displacement vector and the force vector, you just simply take the dot product, you can get the work done that way. But remember, the generic definition of work involves an integral between force and in terms of a position. And that is, by the way, equivalent to change in kinetic energy of the system. Okay, and work is what causes that. All right, so thank you everyone for your attention, and until the next lecture, let me know if there's any questions. You can always stop by during my office hours. I will post your homework assignments related to this lecture and the lecture slides and my notes. So stay safe out there, and then see you next time.